Hello students, this is Mr. Ezra. Unfortunately, I'm not at school today, so I am leaving this video for you. And it is about the standard normal distribution. In the video, as I'm kind of working through problems and showing you examples, you're going to need a few things on your desk. First, you need your graphing calculator. This is the TI-84 Plus or the TI Nspire or something like that. Now, if you don't use the TI-84 Plus, you kind of have to figure out how to do these things on your own, but most of you have gotten pretty good at kind of working those processes out. The other thing that you need on your desk, aside from your notes and your paper and all of that normal stuff, is that I think it was yellow, but that paper that had a whole bunch of numbers on it that was the standard normal table. You'll need that as well. And with those things in hand, let's talk about the standard normal distribution. Last week we began to discuss normal distributions and we learned something called the empirical rule, also called the 68, 95, 99.7 rule. And this is a general pattern that normal distributions follow, where 68% of all data is within one standard deviation of the mean, 95% of all data is within two standard deviations of the mean, and 99.7% of the data is within three standard deviations of the mean. This rule is not, it's not exact. Your data is not going to follow it exactly, but it's going to be pretty close. And we even went further, hopefully, in our notes and began to break that up and look at each of those sections separately and what percent would fall into each section. And having a copy of this might help you when you get to problems where you're using the empirical rule because, for example, with our data set here, what I did with this data set is I hit Stat right there, Edit, and I typed all of those numbers into List 1. All those numbers into List 1. I then hit Stat, Calc, 1var stats. And it defaults to List 1, so you can hit Enter here, but if it helps you to always remember to put where your list is, you can also do that. I was in List 1, so I'm going to hit 1var stats of List 1. And I hit Enter, and it gives me a mean and a standard deviation. So my mean is 95.7, so that should be a 95.7. That's the mean. That's the center of the distribution. If I add the standard deviation of 30.7, and I'm estimating these, I add it 3 times to the right, and I subtract it 3 times to the left, what I'm going to get is an idea of what this distribution looks like, an idea of what the picture of this distribution looks like. Assuming that this data follows a normal distribution, I could say that I am confident that about 34% of the data falls between 65 and 95.7. Or I am confident that about 50% of all of the data is less than 95.7. I'm confident that 13.5% of the data is going to fall between 126.4 and 157.1. So knowing where each of these numbers falls under my normal curve can help me to know, what percent of my data falls between two of these standard deviations from the mean, from two of these numbers. Now, we have talked before about something called a z-score. Remember that z-scores are standardized scores, and we've learned the formula for finding z-score is z equals x minus mean divided by standard deviation. This is mu for mean, sigma for standard deviation. And that's what I've done here with the z-score for 82. I've subtracted the mean and divided by the standard deviation, and I got a z-score of negative 0.45. Well, the standard normal distribution is special. Whereas if I were to list these numbers underneath the curve, for every single problem, the numbers could look different. I could have a different mean and a different standard deviation, so I'd have to build a different curve for each set of numbers. When we standardize our scores to z-scores, now we have exactly the same numbers under every single curve, and these are the numbers that we're going to use today. The mean of the standard normal distribution, the mean of z-scores is always 0. And because z-scores tell us the number of standard deviations above or below the mean, as I go 1, 2, 3 standard deviations above the mean, my z-scores are 1, 2, and 3. When I go -1, -2, -3 standard deviations below the mean, then they're what they are because of the definition of what a z-score is. So this is going to make life a lot easier for us because we're not going to have to add 3 standard deviations and subtract 3 standard deviations every time. We will always have the same numbers under here, and I can very quickly find exactly where -0.45 is. It's right here, okay? If it's between the mean and 1 standard deviation to the left of the mean, okay? It's 0.45 standard deviations below the mean. Now, as we begin to look at these problems, a lot of the time you're going to be asked to sketch the curve. And when you sketch the curve, you'll notice that my curves aren't the most beautiful curves in the world. And I've had a lot of practice, and they're not necessarily easy to draw, but you want to do your best, okay? You want to make it mound-shaped symmetric to the best of your ability. You can get kind of a good-looking curve from your notes and kind of trace it if you need to. But we can use this empirical rule at times to find areas under the curve. For example, if I want to know the area to the left of a z-score of 2, well, since I know the z-score numbers under the curve are always the same, I find 2 and I shade to the left. This is sketching the curve. Sketching the curve involves also shading the curve. Now, if I kind of get this bigger picture over here, let's see if I can make this a little bit bigger for you. So let's say we had this picture here, and in our notes, and we wanted to go to the left of 2. Well, you can see that to the left of 2, standard deviation is the right is 13.5%, 34%, 34%, 13.5%, 2.35%, 0.15%. One way to answer this question is to add all those percentages together until we get the sum. Alternately, if you add the 2 above 2 standard deviations, which might be a little quicker, that's going to be 2.35 plus 0.15, it's 2.5%. I can subtract that from 100% to get 97.5%. So there are some shortcuts that you can take here. Sometimes it's easier to use the complement instead of adding them all up together like I did here in this example. But either way should get you the same answer. Another thing that you can do when you're using the empirical rule is, for example, this says find the area to the right of z equals -1. Well, I know that the area to the right of z equals 0 is 50% because half of the curve is above that. If I add the 34% that I know is between 0 and -1, I get 84%. So it's pretty quick to do that. Looking at the next example between a z of -2 and a z of +3, I could add the 13.5% plus 34% plus 34% plus 13.5% plus 2.35%. That's one way to do it. I could also subtract out the things that I'm not shading from 100%. Either way, I should get 97.35%. And from between z equals 0 to z equals -3, shading to the left of 0, it's almost 50%, but there's this little 0.15% over here that is not included. So you should get 49.85% if you were to work those problems out. It's a good idea to have a good curve like this sketched in your notes. If you don't have it already, you might want to add it in before you go any further. Now, there's a reason that I asked you to get your calculator out today and to get your table out today. What do you do if your z-score is not an integer? In other words, it's not 1, 2, 3, or -1, -2, -3. Well, in this case, we can't use the empirical rule. We have to use something else. So I'm going to show you 2 approaches to this. If you have a graphing calculator, you should use your graphing calculator. It's going to be faster, easier, you're going to get used to it, you're going to like it. You've got to practice it before you get to your quiz or test. so that you know what you're doing. The command that we're going to look for in our calculator is called normal CDF. Normal CDF allows us to find the cumulative frequency, or the area under the curve between two boundaries. Okay, so the command is going to be normal CDF, lower boundary, comma, upper boundary, comma, mean, comma, standard deviation. Now, where do you find normal CDF in your calculator? There is a button called vars. It's not the part of the calculator we're going to choose. Instead, we want the command above vars, which is DISTR, which stands for distributions, because the normal distribution is a type of distribution. So you have to hit second vars to get to that distribution command. The second command is called normal CDF. Skip over normal PDF. It is not something that we will use for this course. If you want to ask about it later, I'll try to tell you about it, but it's really not something that we want to worry about. We want to use normal CDF. So we choose that. Now, if you have a new operating system on your calculator, like you brought your calculator this year, there is a chance that it may ask you questions instead of you having to type in commas. So it might ask, what's the lower boundary, what's the upper boundary, what's the mean, what's the deviation. You'll fill those things in and then click calculate or paste. If you have a calculator like me, you've got to type these things in. So we want to go to the left of a z-score of negative 1.93. It just so happens that as we keep going to the left of negative 1.93, we're going towards negative infinity, but of course we'll never reach there, and there's a bit of a problem. Our calculator doesn't have the ability for us to type in infinity, so we choose something that is a really big negative number that's as close to a negative infinity as our calculator will allow us to, and it's 1e99, or negative 1e99. Now the e is right above this comma here, so you're going to hit second comma to get the e, and then 99. This is your calculator's method of typing in scientific notation. So it's really like saying a negative 1 with 99 zeros after it. That's a very large negative number, and certainly it's going to be super far to the left of negative 1.93 under the standard normal curve. I then want to put the right boundary. Now the right boundary is negative 1.93. And then I'm going to put comma, mean, comma, standard deviation, which will always be 0 and 1 for the standard normal distribution. I get an area to the left of a z-score of negative 1.93 of 0.0268. If you were to write that as a percent, it would be 2.68%. I want to go to the right of 1.11. I want to know the area under the curve to the right. Again, I'm going to use normal CDF, but I will put in the left boundary. The right boundary is approaching infinity, but I can't put that in my calculator, so I use a really big positive number, 1e99, which again is 1 times 10 to the 99th power, or 1 with 99 zeros after it. Now, we'll go ahead and do this, but then I want to go back and look at how to do these if you don't have your graphing calculator with you. So we'll normal CDF 1.11, comma 1e99, comma 0, comma 1. And we got 0.1335 rounded. And you can round these 4 places past the decimal. That will be just fine. That'll be just fine. So, question. What if I don't have my calculator? What do I do, Mr. Ezra? Well, you're forced to use this table. It's called the standard normal cumulative probability table in your notes. And what we're going to do is we're going to look for this z-score in our table. This z-score right here. So I'm going to look for the z-score of negative 1.93. When I do this, the first thing I want to point out is this table is always shading to the left. So we are only going to be, all of these areas inside the table represent area to the left of some z-score. So we want to look up negative 1.93, what we're going to do is we're going to find the negative 1.9 on the left, right here. And the 3 is going to come from the top. So we're always going to go 2 places past the decimal. The ones place and the tenths place is going to be on the left side. The hundredths place is going to be at the top. And when you put those together, negative 1.93, the intersection is the answer. So we should get an answer of pretty close to 0.0268 or 2.68%. Let's see if that's what we got, 0.0268. So using the table is pretty easy once you get used to it. You just have to find the left side, the first 2 digits on the left side, and then the last digit on the top, and you're good to go. Now, we mentioned that the table always has the area to the left shaded. So what that means is when we get a question like this one that says to the right of a z of 1.11, what we have to do in our table is we're still going to find positive 1.11. See, 1.11 is going to be, let's see if we can get this, 1.1 right here on the left, 0.01 on the top, where they intersect is 0.8665. Now, what we're going to find out is that's not the answer, right? We got 0.8665. Why isn't it the answer? Because that's the area to the left of 1.11. If we want to find the area to the right, we're going to have to subtract that from 1. And when we do that, we're going to get 0.1335. So area, when you're using your calculator, it's left boundary, right boundary. You have to think about those boundaries. And if you can't put infinity in, you use negative 1e99 or positive 1e99. In the table, it's always going to be to the left. So on the left tail, you just look up that z-score in your table. You're done. For a right shaded curve, you're going to look up that z-score, but subtract whatever area you get from 1 to get the correct side of the graph. Now, when it asks for between 0 and 2.34, in our calculator, it's pretty simple. We use this normal CDF command, same exact command, but now we have a lower boundary of 0, comma, upper boundary of 2.34 with a mean of 0 and a standard deviation of 1. So we very quickly, still using the same exact command, get the answer of 0.4904. In the table, what you're going to have to do is look up the z-score of 0, look up the z-score of 2.43. Let's go ahead and do that. It's actually 2.34. Okay, so we'll start with 2.34. 2.3, there we go. 2.3 is over here. There's 4 at the top of this row, so 0.9904. So we 0.9904. And then hopefully you know the area to the left of 0, but if you don't, you can find 0, 0 in your table and you'll see that it's 50% or 0.5. So we get 0.5. What has to happen in our table, our calculator goes straight to the answer, but our table, we have to find the area to the left of 2.34 and subtract out the area to the left of 0. And by subtracting out that area, what's left behind is going to be our shaded region of 0.4904. So you've got to think when you're using your table of how to use the table to achieve the desired area. Your calculator goes straight there. For this last one, we're just going to use our calculator really quickly to get the answer. All right, we got 0.8792. I should probably point out too that your curves aren't going to be perfect because you're sketching these and no one has the ability, well, I'd say very few people have the ability to sketch a perfect curve, one that looks just right. But you can look at the amount of shading in your curve and say, oh, yeah, that looks like about 50%, or oh, yeah, that's about 90%, or oh, yeah, that's about 2 or 3%. But if you shaded a ton of your curve and you only get 2 or 3%, or you shaded very little of your curve and you get like 87%, well, there's a problem there. And it's either in your calculations or the sketching of your curve, but those things should kind of match up. These problems you need to copy down onto your notebook paper and try them on your own. You can use your calculator, you can use your table, you can use both. But these problems are going to be due on Wednesday. So I want you to copy them down and try them and have them ready for class on Wednesday. Really quickly, I want to add on one more thing. We just finished a chapter on probability, and I want you to understand that when we talk about the probability of a normal distribution curve, the truth about all density curves, and the normal curve is a type of density curve, is that the area under the curve is always 1. Well, this corresponds that the probability of every single possible outcome in a probability distribution is also 1. So there's this direct link here. When we're finding the probability of z is less than 1.34, we're just finding the area under the curve for the z-score of less than 1.34. So we're still either going to use normal CDF or we're going to go to our normal table and find 1.34, which you can see this can be pretty fast, 0.9099. Let's see if we get that in our calculator. -1 E99, comma 1.34, comma 0, comma 1. Yep, 0.9099. So in this case, the table was a little bit faster, wasn't it? But in general, it's best to choose a method and stick with it. And I think that the calculator always works. You know, you just have to put your left boundary and your right boundary in correctly. We have one more example here. When we find the probability that we get a z-score between -1.2 and +2.56, we're just finding the area between those points. So we are going to use normal CDF from -1.2 to +2.56 with a mean of 0 and a standard deviation of 1, and we get a probability of 0.8797 rounded. I want you to understand that this isn't different. It's the same thing that we have been practicing, you just have this probability notation attached to it. Again, I have a few more problems for you to try. So if you will copy these down onto the same place in your notebook where you wrote down the other problems, try these 5 probability problems using either your calculator or your table and have them ready to turn in on Wednesday. Well, ladies and gentlemen, that is it for today. So hopefully you at least are able to use your calculator and your table to find these area under the curves for the standard normal curve. We will talk a lot more about this in class when I return on Wednesday. I will see you then.